Right now, a photon fired in a laboratory changes what it was doing billions of years ago. That is confirmed. Scientists have run the experiments. The results keep coming back the same. The future reaches into the past and rewrites it. We will visit the chamber where a particle's history changed after it already happened, a thought experiment that used starlight from before Earth existed, a handshake between emitter and absorber traveling backward through time, and the theory that the present moment is never fully real until the future locks it in. If that reshapes your reality, subscribe. This channel was built for that moment. Open your mind. We begin. A single particle of light crosses a detector screen, and somewhere in the foundations of physics, everything we thought we knew about time quietly begins to crack. The setup looks innocent enough. A photon, the smallest possible package of light, is aimed at a barrier with two narrow slits cut into it. When nothing watches which slit the photon uses, something extraordinary happens. The photon spreads like a wave, passes through both openings at once, and produces a rippling striped pattern on the screen behind the barrier. Bands of light and shadow. A pattern that can only exist if the photon traveled every possible path simultaneously, interfering with itself the way ripples on water interfere with each other. Now, place a detector at the slits. Record which path the photon takes. The striped pattern immediately disappears. The photon snaps into a single definite trajectory. Wave collapses into particle. The act of observing changes what the particle does. That part physicists settled decades ago. Strange, but accepted. What comes next is where the ground gives way. In the version of this experiment that has shaken physics to its foundations, the photon is created alongside a partner. Through quantum entanglement, the two particles share a connection that persists regardless of distance. The original photon, called the signal photon, travels through the double-slit apparatus and strikes the detector screen. It has already landed. Its arrival position is already recorded. The data is already written down. And then, after that, a measurement is made on its partner. What that later measurement reveals produces a result that should be impossible. When physicists sort back through the earlier data and filter it by what the partner photon's future measurement showed, the interference pattern in the original photon's data changes. Wave behavior appears in one sorted group of past events. The fringes vanish from the other. The future measurement determines which subset of already recorded past events shows wave behavior and which shows particle behavior. This is the delayed choice quantum eraser. It has been performed in laboratories across the world by independent research groups. The results are confirmed. The effect does not go away. And sitting at its center is an implication that no one has been able to fully dismiss. A choice made after the signal photon already arrived appears to reach backward and reorganize what that photon was doing in the past. Sit with that for a moment. A particle lands on a screen. Its position is logged. Time moves forward. A separate measurement is made on a different particle, and the first particle's historical behavior, the thing that had already happened, correlates with a decision that had yet to be made. Every assumption baked into the word before is under pressure here. Every instinct that says the past is closed, that what has happened cannot be touched by what comes later, is exactly what these numbers quietly contradict. Some physicists will tell you the statistics explain it cleanly. Others, researchers with careers built on Nobel-connected work, will tell you the universe is telling us something profound and terrifying about the nature of time itself. Both sides agree on the experimental results. What they cannot agree on is what those results mean. And that disagreement turns out to be one of the most consequential arguments in the history of science, because the data goes deeper than anyone expected. Here is the part that popular accounts almost always get wrong, and getting it right is what makes the mystery even stranger. When you look at the raw data from the signal photon detector, the screen where the first photon lands, you see nothing unusual, no interference pattern, no fringes. Just a smooth, featureless spread of dots that looks exactly like what you would expect from particles behaving classically. An outside observer watching that screen in real time would notice nothing strange at all. The strangeness only appears when you do something specific. You take the partner photon's measurement results, the ones that came later, and you sort the original data by those outcomes. You divide the first photon's arrival points into groups based on what happened afterward to its partner. When you do that, something extraordinary emerges from the noise. Certain groups of past events suddenly reveal an interference pattern. Others show no pattern at all. The sorting key is entirely the future measurement. Physicists call this post-selection. The future determines which sub-ensemble of past events shows wave behavior. This detail is critical, and it has two enormous implications that pull in opposite directions. The first implication is that no usable signal travels backward in time. A physicist sitting at the signal screen in the past cannot look at the raw data and extract any information about what the future measurement will choose. The pattern is invisible until the future data arrives and provides the sorting key. This is confirmed. Quantum mechanics protects itself. No experimenter in the past can exploit this effect to receive a message from the future. The correlation exists, but it cannot be weaponized for communication. The second implication is what makes the effect so haunting. The correlation genuinely exists. The subset of past events that will later be tagged as erased really does show interference. The subset tagged as which path preserved really does show no interference. The sorting reveals a structure that was already present in the historical data, invisibly organized by an outcome that had not yet occurred when the data was recorded. Think of it as a library of past events, already written and sealed. The future measurement does not add new pages. It provides the index that reveals which pages always belonged to which chapter. The organization was there all along, waiting for a future event to make it visible. That image is either deeply reassuring or deeply disturbing, depending on your philosophy of time. If the past data was always structured that way, always containing the interference pattern in that specific subset, then something about the future measurement was already encoded in the past. The present was not fully determined by what preceded it alone. A future boundary condition was involved. Physicists who defend the standard interpretation say this proves nothing about backward causation. The correlations arise from entanglement, they argue. An entanglement is a feature of quantum systems established at the moment the particle pair was created. The future measurement simply reveals correlations that were always there. Physicists who push the retrocausal interpretation say, yes, exactly. The correlations were always there, and that is precisely the problem. Because something had to put them there, organized by an outcome that had not yet happened, the data is unambiguous, its meaning is not, and that tension is about to get much older and much stranger. Before there were laboratories testing this effect, there was one physicist asking a question so extreme that his colleagues initially thought it was a provocation. John Archibald Wheeler was not a man who thought small. He coined the term black hole at a time when most physicists considered such objects too bizarre to take seriously. He supervised Richard Feynman's doctoral research. He coined the phrase quantum foam to describe the churning geometry of spacetime at the smallest possible scales. And in 1978, he proposed a thought experiment that seemed, at first, almost scandalous. Wheeler asked, what if we delay the choice of how to measure a particle until after it has already cleared the critical point in the apparatus? What if the decision about whether to observe wave behavior or particle behavior comes after the photon has already committed, or supposedly already committed, to its path? Quantum mechanics gave a clear and deeply unsettling answer. The particle's past behavior would be determined by the future choice of measurement. The photon would not have had a definite history, wave or particle, until an observer's later decision locked that history into place. Wheeler did not stop at laboratory scales. He extended the thought experiment to the cosmos. Consider a quasar, an extraordinarily luminous object, billions of light years away, powered by matter falling into a massive collapsed body at its center. Its light travels across the universe toward Earth. Along the way, it passes a galaxy sitting between the quasar and us. Gravity from that galaxy bends the light, splitting it into two separate paths that curve around the galaxy on opposite sides, and both eventually reach Earth. This is gravitational lensing, and it is confirmed by observation. Wheeler realized this was a cosmic version of the double slit. The light from the quasar travels two distinct paths to reach us. And an astronomer on Earth, billions of years after that light left its source, gets to choose how to detect it. Place a telescope pointed at one side of the lensing galaxy, and you detect the photon arriving via that specific path, particle behavior. Set up an interferometer that combines the light from both paths, and you see the interference fringes of wave behavior, revealing that the photon traveled both routes simultaneously. Here is the part that stops you cold. That photon left its source billions of years ago, before Earth existed, before the solar system coalesced, before the first single-celled organisms appeared in the oceans of a young planet. And yet, Wheeler argued, the astronomer's choice of instrument today appears to determine what that photon was doing at the moment it left the quasar. The past, reaching back further than any human concept of history, is apparently not finished being written. Wheeler himself put it plainly. He said, "The past has no existence except as it is recorded in the present." He did not mean this as poetry. He meant it as physics. The universe, on this reading, does not record its history until observers in the present make choices that lock that history into place. Every measurement we make is an act of creation, retroactively, across whatever time has elapsed. And the implication is one that the scientific community has been quietly wrestling with ever since. What happens when someone actually builds the device to test it? For nearly 3 decades, Wheeler's delayed choice experiment lived entirely in the imagination. A thought experiment, vivid and disturbing, but safely confined to the realm of theoretical possibility. No laboratory had yet built a version precise enough to test whether the quantum world actually behaved the way Wheeler predicted. That changed in 2007. A team of researchers in France, working at the Laboratoire Charles Fabry de l'Institut d'Optique in Palaiseau, constructed the first working delayed choice apparatus capable of genuinely testing Wheeler's prediction. The team was led by physicist Vincent Jacques, and the experiment they built was a precise and careful piece of engineering. The core challenge was timing. Wheeler's thought experiment requires that the choice of measurement be made after the photon has already passed the critical decision point in the apparatus, the point where it would have to commit to traveling one path or both. Any signal about the upcoming measurement choice must be kept from reaching the photon by any means, including light speed signals, before that commitment point. The French team solved this by using a quantum random number generator to determine the measurement setting in real time, after the photon had already entered and passed through the first beam splitter of their interferometer. The random number generator produced an unpredictable output that switched the apparatus between 2 configurations. In one configuration, the experiment revealed which path the photon took, particle behavior. In the other, the paths were recombined, allowing interference, wave behavior. The switching happened so fast, and the timing was so carefully engineered, that no light speed signal could have traveled from the measurement choice back to the photon's entry point in time to influence the photon's behavior there. The photon, in other words, was already past the point of no return when the measurement decision was made. The results came back exactly as quantum mechanics predicted. The photon's behavior correlated perfectly with the future measurement setting. When the apparatus was switched to reveal which path information, particle behavior. When switched to allow interference, wave behavior. The correlation held with a statistical confidence that ruled out chance. The photon's past behavior matched a choice that had not yet been made when it entered the apparatus. This was no longer a thought experiment. This was hardware on an optical bench with photons and electronics and peer-reviewed results published in the journal Science. And the researchers were careful about their language. They did not announce that the future causes the past. They reported what they measured, that the photon's behavior was correlated with a future setting in a way quantum mechanics predicted, and classical physics cannot explain. But the correlation was real, the timing was airtight, the statistics were decisive. Consider what the random number generator actually guaranteed. Its output was unpredictable even in principle. No hidden variable, no pre-existing pattern, no information from the past could have told the photon in advance which measurement setting to expect. The choice was genuinely undetermined when the photon entered the apparatus, and still, the photon's past behavior correlated with it. Physics had moved the delayed choice experiment out of the realm of philosophy and into the realm of confirmed experimental fact, which immediately raised the next question. If the effect held in a laboratory using photons traveling a few meters, what would happen when the distances became much, much larger? The answer came from orbit. 8 years after the French laboratory result, a team in Italy decided to find out whether the delayed choice effect would survive a test on a scale that would have made even Wheeler pause. The experiment, conducted by researchers at the University of Padua and published in 2016 in the journal Science Advances, sent photons on a round trip to a satellite orbiting 1,500 kilometers above Earth. The key challenge was the same as in the French experiment, but amplified enormously by distance and travel time. The measurement choice had to be made after the photon had passed the critical entry point of the apparatus, and no signal about that choice could reach the photon in time to influence its behavior there. At the scale of a laboratory bench, this timing constraint requires electronic switching faster than nanoseconds. At the scale of a satellite 1,500 kilometers away, the constraint becomes something else entirely. The photon travels to the satellite and back, and during that entire journey, the measurement setting must remain unknown to it. The choice of how to detect the returning photon must be made while the photon is still in transit. The Italian team used a random number generator to determine the measurement setting while the photon was traveling. And here is the feature that made this experiment particularly powerful. The event of making the measurement choice was what physicists call space-like, separated from the event of the photon entering the apparatus. In the language of special relativity, no signal traveling at the speed of light or slower could connect the two events. They were too far apart in both space and time for any conventional influence to pass between them. This rules out a whole class of explanations. If someone wanted to argue that the future measurement somehow signals backward through a hidden channel, the Italian experiment closes that possibility. No physical signal of any known kind could have carried information about the upcoming measurement choice to the photon at the moment it entered the apparatus. The results matched quantum mechanical predictions precisely. The delayed choice effect persisted across space-like separations. The photon's behavior correlated with a measurement choice made too late and too far away for any classical explanation to account for. Across 1,500 kilometers of empty space, in one of the most demanding experimental tests of quantum mechanics ever conducted, the effect held. What this means in simple terms is this. Whether you test the delayed choice prediction with photons crossing a few meters of optical bench, or with photons bouncing off a satellite, the result is the same. The past behavior of a photon correlates with a future measurement choice that could not have reached the photon in time by any known means. The universe seems to insist on this result regardless of the scale at which you test it. That insistence is itself significant. It suggests the effect is not a laboratory artifact or a quirk of small-scale physics. It appears to be a fundamental feature of how reality operates. The question that remained was whether anyone could explain, in precise mechanical terms, exactly how the correlation was achieved. One experiment attempted to lay out the full machinery of the effect in extraordinary detail, and it produced a result that, once understood, refuses to leave you. To understand what is genuinely strange about the delayed choice quantum eraser, you need to see the full apparatus, step by step, because the devil is entirely in the details. The experiment, first performed by a team led by Huw Kim and Marlon Scully, and published in 2000 in the journal Physical Review Letters, begins with a source that produces pairs of entangled photons. Each pair consists of a signal photon and an idler photon, born together and connected by quantum entanglement. The signal photon travels forward and passes through a double-slit barrier. It then strikes a detector screen. This is the photon whose interference pattern we want to study. The signal photon arrives at the screen first. Its landing position is recorded. The experiment's clock, so to speak, has already ticked past the moment of measurement for this photon. The idler photon takes a longer, more complicated path. It travels through a series of optical components that route it toward one of 4 possible detectors. 2 of those detectors, labeled here as the preserving detectors, receive the idler photon in a way that retains the witch path information. If the idler photon reaches one of these detectors, you can in principle determine which slit the signal photon used. Knowledge of the path is preserved. The other 2 detectors, call them the erasing detectors, receive the idler photon after it has passed through a beam splitter that mixes the 2 possible paths together. When the paths are mixed, the witch path information is destroyed. It is quantum mechanically erased. There is no longer any way, even in principle, to determine which slit the signal photon used. Now here is the timing that makes this extraordinary. The idler photon takes a longer route. It arrives at its detector after the signal photon has already hit the screen. The witch path information is either preserved or erased by an event that happens after the signal photon's position has already been recorded. When physicists sought the signal photon's landing positions by which idler detector fired, they find something that should stop any reasonable person cold. The signal photons whose idlers ended up at the erasing detectors form an interference pattern. Wave behavior, recovered. The signal photons whose idlers ended up at the preserving detectors show no interference, particle behavior. The signal photon's pattern, already recorded, depends on what happened to its partner afterward. One important clarification, and this matters enormously: the raw, unsorted data at the signal screen shows no interference pattern. Nothing special appears there in real time. The organized structure only becomes visible when the future idler data is used to sort the past signal data. No observer sitting at the signal screen in the present could exploit this to receive a message from the future. Quantum mechanics is consistent in this respect. The effect is real but cannot be used for signaling. That protection does nothing to resolve the deeper mystery. The structure exists in the past data. It is organized by the future. Something about the future boundary condition of this experiment shaped which past photon arrivals belong to which group. The question of how that organization got there, who or what imposed it on events that had already occurred, is the question at the heart of everything that follows. Several physicists have proposed answers. They disagree profoundly, and the first challenge comes from the most established tradition in quantum mechanics. Before accepting that the future changes the past, it is worth asking whether that conclusion is actually forced on us by the experiments. For many physicists, the answer is a firm no, and their argument deserves full attention. The most powerful alternative framework is the Copenhagen interpretation, which has been the default language of quantum mechanics for nearly a century. It was developed in the 1920s by Niels Bohr and Werner Heisenberg, and its central claim is both simple and radical. Quantum mechanics does not describe what particles are doing when no one is measuring them. It only describes the outcomes of measurements. Under this view, asking what the signal photon was doing before it hit the screen, whether it was a wave or a particle, whether it took one path or both, is simply a category error. The question has no answer because it has no meaning. There is no what the photon was doing. There is only what the detector registers when a measurement is made. This is confirmed to be mathematically consistent. Every prediction of the delayed choice experiments can be derived from standard quantum mechanics without invoking backward causation. The equations work. The results match. The framework is internally coherent. From the Copenhagen perspective, the delayed choice quantum eraser is not strange at all, or at least, it is no stranger than any other quantum measurement. The signal photon did not have a definite history waiting to be influenced. It had no history at all in the classical sense. It existed as a superposition of possibilities until measurement forced an outcome. The idler photon's later measurement is simply part of the larger quantum system being resolved. No information traveled backward. No cause ran the wrong direction through time. The correlations exist because the two photons are entangled. Entanglement connects their measurement outcomes regardless of timing. The future measurement and the past measurement are not in a causal relationship. They are correlations arising from a shared quantum state established when the photons were created. This objection has real force. Generations of brilliant physicists have found Copenhagen satisfying precisely because it is disciplined. It refuses to speculate beyond what the mathematics requires. It says, the equations give the right answers, so stop asking what is really happening underneath. But a growing number of physicists and philosophers find this response unsatisfying in a specific way. Science has historically made progress by asking exactly those forbidden questions. Do not ask what is really happening has the uncomfortable shape of a prohibition designed to protect a framework from scrutiny. And there is a deeper problem. The Copenhagen interpretation says there is no path, no decision, no past state to influence. But if that is true, then the detailed structure we find when we sort the data, the interference pattern precisely correlated with the future erasing event, needs an explanation. Where did that structure come from? If the photon had no history, why does the history-shaped structure appear when the future data is applied? The Copenhagen response is that this question also has no meaningful answer. Some physicists find that intellectually honest, others find it evasive. One physicist decided the universe was trying to tell us something specific and developed a mathematical framework to capture it. Yakir Aharonov has spent more than 60 years asking the question that Copenhagen forbids, not what does the detector register, but what is actually going on between measurements. And his answer, developed over decades with collaborators, including Lev Weidmann and Peter Bergman, is mathematically precise, experimentally testable, and philosophically radical. Aharonov received the Huw Prize in Physics, one of the most prestigious awards in science, and the United States National Medal of Science, in part for this work. His framework is called the two-state vector formalism. Understanding it is worth the effort because it offers the most systematic, theoretical treatment of the strange correlations we have been examining. Standard quantum mechanics describes a particle using a single mathematical object called a wave function. This wave function evolves forward in time from the moment the particle is prepared. The preparation is the past boundary condition. The wave function tells you the probabilities of different measurement outcomes if you measure now. It says nothing, officially, about what happens after. Aharonov's framework says this is incomplete. A full description of a quantum system between two measurements requires two wave functions, not one. The first evolves forward in time from the initial preparation. The second evolves backward in time from the final measurement. The present state of the particle is shaped simultaneously by both boundary conditions, what came before and what comes after. This is not speculation. It is a mathematical framework that is provably equivalent to standard quantum mechanics in its predictions for all experiments. You cannot distinguish the two-state formalism from Copenhagen by any measurement outcome alone. They agree on every number. What differs is the picture of reality they paint. In the standard picture, the particle's state is entirely determined by its past. In Aharonov's picture, the particle's state between measurements is determined by both its past preparation and its future measurement outcome. The future boundary condition is as real and as causally relevant as the past one. In Aharonov's own words, delivered at a major physics conference, the state of a quantum system at any given moment is described by two wave functions, one evolving from the past to the future, and one evolving from the future to the past. This is ontologically radical, even though it is mathematically conservative. It takes the equations physicists already use every day and insists that both solutions, the forward-evolving one and the backward-evolving one, are physically real descriptions of what the particle is actually doing. The framework does not add new mathematics. It adds the courage to take the existing mathematics seriously. The delayed choice experiments fit naturally into this picture. The signal photon's past preparation and the idler photon's future measurement are both genuine boundary conditions on the present state of the entangled system. The correlation between them is not mysterious. It is the expected outcome when two boundary conditions constrain the same physical system from opposite ends of time. But Aharonov went further. He realized that if the future boundary condition is real, it should produce measurable effects in the present that cannot be explained by past preparation alone. Effects that should be physically impossible by ordinary quantum mechanics. Effects that, when the experiments were actually run, turned out to be exactly as bizarre as predicted. The future was leaving fingerprints. The strangest prediction of Aharonov's two-state formalism involves a technique so delicate it barely disturbs the particle it touches. And what it reveals about that particle is something quantum mechanics says should be impossible. In a standard quantum measurement, the act of measuring forces the particle into a definite state. You learn something, and in learning it, you change the system. This is the measurement problem at the heart of quantum mechanics. You cannot observe a quantum system without altering it. Aharonov and his colleagues, including David Albert and Lev Vaidman, asked what would happen if you made your measurement extremely gentle. So gentle that it barely nudged the particle, providing only a tiny hint of information about its current state without forcing it into a definite outcome. Then, after this soft intermediate measurement, you proceed to a final strong measurement, a post-selection. In this sequence, the particle is prepared in a known initial state, gently probed, and then subjected to a final measurement that selects only a specific outcome. The gentle intermediate measurement produces a number. Aharonov called it the weak value of the measured quantity. What should that number look like? For a standard property like spin, quantum mechanics defines a clear, allowed range. A spin 1/2 particle can have spin values of positive 1/2 or negative 1/2 in any given direction. Those are the only possibilities. That is established physics. In 1988, Aharonov, Albert, and Vaidman published a paper in Physical Review Letters showing that weak values can fall dramatically outside this allowed range. The same spin 1/2 particle, probed gently enough between a specific preparation and a specific post-selection, can produce a measured spin value of 100, a number 100 times larger than the physical maximum allowed by ordinary quantum mechanics. This was an extraordinary claim, and the experiments have been performed across multiple independent laboratories. The bizarre numbers appear exactly as the theory predicts. These anomalous weak values are confirmed. They do not go away when you check them again. What produces them? The key lies in the two boundary conditions. The soft intermediate measurement catches the particle in a state that is simultaneously shaped by its past preparation and its future post-selection. When those two boundary conditions combine in the right way, the intermediate state can take values that neither boundary condition alone could produce. The future measurement reaches back and reshapes what the particle appears to be in the present. This is not a failure of the instruments or a statistical artifact. The anomalous weak values are stable, reproducible, and fully explained by the two-state formalism. They are what you predict when you take seriously the idea that the future boundary condition is a genuine physical influence on the present state of the system, and the implications extend beyond laboratory curiosity. If future measurements genuinely shape present quantum states in this measurable way, then the connection between the delayed choice experiments and real backward causation is stronger than the skeptics suggest. The structure is there, in the mathematics and in the measured numbers. Something from the future is casting a shadow backward into the present. The question is whether that shadow has a mechanism. One physicist spent years building a framework to describe exactly that mechanism. He called it a handshake across time. Every quantum event, according to John Cramer, involves a conversation between the future and the past. Not metaphorically, literally. A physical exchange of waves traveling in opposite directions through time, completing a handshake that makes the event possible. Cramer is a physicist at the University of Washington who developed what he calls the transactional interpretation of quantum mechanics, first published in 1986 in the journal Reviews of Modern Physics. His framework draws on a discovery that Richard Feynman and John Wheeler made decades earlier, a discovery that most physicists quietly set aside because it was too strange to be comfortable. Wheeler and Feynman showed in the 1940s that Maxwell's equations, the fundamental equations governing all electromagnetic waves, have two sets of solutions. One set describes waves traveling forward in time, moving from a source toward its destination in the familiar way light and radio waves propagate. Physicists call these retarded waves. They are what we experience every time we turn on a lamp or speak into a telephone. The other set of solutions describes waves traveling backward in time, moving from the destination back toward the source. Physicists call these advanced waves. They are just as valid mathematically as the forward-traveling solutions. But for generations, theorists discarded them as physically meaningless, an artifact of the mathematics with no reality. Wheeler and Feynman showed that if you include both solutions together in the right way, they can be made to cancel each other in the macroscopic world, leaving only the forward-traveling waves we observe. But in doing so, they preserved the backward-traveling solutions as genuine parts of the physical picture. Cramer took this seriously. He extended the logic to quantum mechanics itself. In his transactional interpretation, every quantum emission begins with an offer wave, the ordinary forward-in-time wave function that travels from the emitter toward potential absorbers. When an absorber receives this offer wave, it responds by sending back a confirmation wave, the complex conjugate of the wave function, traveling backward in time toward the emitter. The emitter receives confirmation waves from every possible absorber simultaneously, each weighted by probability. A transaction is completed when offer and confirmation waves reinforce each other consistently, and this reinforcement constitutes the quantum event, the transfer of energy, momentum, and information. The mathematical elegance here is remarkable. In quantum mechanics, the probability of any transition is written as the absolute square of the wave function. That expression is the product of the wave function and its complex conjugate. In Cramer's framework, this is literally the product of the forward offer wave and the backward confirmation wave. The calculation that every physicist uses daily, without thinking about its meaning, already contains the backward traveling wave built in. The future is already inside the mathematics. Cramer is arguing that this is not a coincidence. The transactional interpretation explains the delayed choice experiments naturally. The future measurement apparatus determines which confirmation waves are available. Those confirmation waves travel backward and shape which transactions are possible in the past. The photon's past behavior is constrained by what the future measurement makes coherent. It is a complete picture, internally consistent, and it requires no collapse, no many worlds, and no prohibition on asking what happens between measurements. It does require something most physicists find uncomfortable, that the future is already participating in every quantum event, silently, invisibly, through a handshake no instrument can directly observe. And this framework did not arise in isolation. It connects to a much older and deeper question about the laws of physics themselves. In 1945, two of the most brilliant physicists alive sat down together and wrote a paper that should have upended everything we thought we knew about time. John Archibald Wheeler was 34. Richard Feynman was 27. The paper carried a dry, technical title, Interaction with the Absorber as the Mechanism of Radiation. Inside it was something extraordinary. When you write down Maxwell's equations, the fundamental laws that govern how light propagates through space, you get two solutions. Two mathematical answers, both perfectly valid. The first describes a wave traveling forward in time, from a source outward into the future. Physicists call this the retarded wave, and it is the one we normally work with. The second describes a wave traveling backward in time, arriving before it was sent. Physicists call this the advanced wave. For decades, the standard move was to throw it away, label it as unphysical, and move on. Wheeler and Feynman refused to throw it away. Their absorber theory proposed something startling. Both solutions are real. When a charged particle emits radiation, it does send a wave forward in time in the ordinary way. But simultaneously, every absorber in the universe, every electron or atom that will eventually receive that energy, sends a wave backward in time toward the source. These future echoes arrive at the emitter exactly on time, and together with the forward wave, they produce the radiation we observe. The light you see with your eyes right now is, in this framework, partly the result of a confirmation sent backward through time by every surface that will ever absorb it. Think of it this way. You call out across a canyon, and what you hear as your own voice is actually the canyon walls answering you back. Wheeler and Feynman were saying, every act of emission is a conversation across time. The future replies first. This was mathematically consistent. It was a legitimate solution to equations that had been verified millions of times, and for most of the 20th century, it remained a curiosity, filed away because nobody could figure out how to test it. Then John Cramer looked at quantum mechanics and noticed something hiding in plain sight. In quantum theory, the probability of any transition is calculated by multiplying the wave function by its own complex conjugate. That mathematical operation, something every physicist performs automatically and without thought, takes a wave that oscillates forward in time and produces its mirror image, a wave that oscillates backward. The calculation physicists use every single day already contains a ghost of the Wheeler-Feynman advanced wave. It was built into the formulas from the beginning. Cramer took that ghost seriously. He proposed that the complex conjugate is not a calculation trick at all. It is a real physical wave, traveling from the absorber back toward the emitter, completing a handshake across time. This is the foundation of the transactional interpretation of quantum mechanics. Every quantum event is a transaction, a deal struck between a source and a detector, sealed by waves moving in both temporal directions at once. The mathematical structure that generates quantum probabilities, one that physicists everywhere write down without a second thought, was already whispering about the future, changing the past. But here is what makes this even stranger. Cramer's interpretation was elegant, even beautiful. Yet elegance is not enough. Physics demands something harder, proof. And the proof, when it came, arrived not from Cramer's direction at all. It came from a philosopher who asked a question so simple that generations of physicists had simply walked past it. The question Huw Price asked sounds almost too obvious to be worth asking. He was a philosopher of physics at Cambridge, a careful thinker, with a background strong enough to engage with the mathematics rather than merely narrate it. The question he posed, which he published in a landmark paper in 2012, was this: if the fundamental laws of physics treat the past and the future identically, why do we assume that causes can only run forward? The answer most people give is that the laws do not treat them identically. Time flows one way, causes precede effects. The past is fixed and the future is open. Everyone knows this. Except that, at the level of fundamental physics, none of it is true. Every equation in the standard model of particle physics works equally well if you reverse the direction of time. Run the mathematics forward and you get a valid physical process. Run the same mathematics backward and you get another valid physical process. Electrons repel each other the same way in either temporal direction. Gravity pulls the same way. Electromagnetic waves propagate with perfect time reversal symmetry. The laws of physics, as best as scientists currently understand them, do not know which direction time is supposed to flow. This is confirmed physics, not speculation. So where does the arrow of time come from? The honest answer is, from the initial conditions of the universe, not from the laws themselves. The universe began in an extraordinarily ordered, low-entropy state. From that starting point, following laws that are completely time-symmetric, systems evolve toward greater disorder. Entropy increases, broken eggs stay broken, smoke disperses into the air. But these are consequences of where things started, consequences of boundary conditions, not mandates written into the laws of nature. And here is where Price's argument becomes genuinely difficult to dismiss. If the laws treat past and future symmetrically, he wrote, then there is no principled reason to allow causal influences in one direction and forbid them in the other. A truly time-symmetric physics should permit causes to run backward just as naturally as they run forward. The fact that we never observe backward causation in daily life is explained by thermodynamics, by the overwhelming statistical weight of entropy increase. It tells us nothing about what is possible at the quantum level, where individual particles operate far below the threshold where thermodynamics applies. Price went further. He argued that if quantum mechanics is to be given a realistic interpretation, one where particles actually exist and have real states between measurements, then retrocausality is required. A time-symmetric realism demands it. The alternative is to pretend that particles have no real properties until measured, which is the Copenhagen position, and which Price regarded as an evasion more than an answer. This is a theoretical argument, not an experimental one. Mark it as such, but it is also one that no one has successfully refuted. The symmetry of fundamental physics is a fact. The direction of causation is an assumption. Price is asking what happens when you take that gap seriously. And then a physicist named Wharton took Price's abstract argument and turned it into a concrete model of how quantum mechanics might actually work. What he found was even more unsettling than the argument itself. There is a way of solving certain mathematical problems that feels deeply strange if you are used to thinking about time as a sequence. In some problems, you know the boundary conditions at both ends, you know the starting state and the finishing state, and you solve for everything in between all at once. You do not step through the problem moment by moment. You treat the entire history as a single object constrained at both ends, and you find the unique solution that satisfies both boundaries simultaneously. Mathematicians call this a boundary value problem. It is how you calculate the shape of a hanging bridge, or the path of light through a lens, or the vibration of a guitar string. You specify both ends, and the middle follows. Wharton, a physicist at San Jose State University, proposed that quantum mechanics is exactly this kind of problem. In the standard picture, quantum mechanics is an initial value problem. You know the starting state, you apply the equations forward in time, and you calculate what comes next. Measurements at the end are treated as revelations of pre-existing facts or as mysterious collapses that the theory never quite explains. The future is the output. Wharton flipped this. In his retrocausal models, the future measurement apparatus is not passively receiving the result. It is imposing a boundary condition. It is constraining what the particle was doing throughout its entire history. The quantum system's evolution between preparation and measurement is solved all at once, with conditions pressing in from both ends of time simultaneously. This is confirmed as mathematically consistent with all quantum predictions. It reproduces every experimental result that standard quantum mechanics reproduces. The difference is entirely in what it says is actually happening. Here is what makes this viscerally strange. In Wharton's picture, the apparatus you set up at the end of an experiment, the detector you place there, the polarizer you rotate, the beam splitter you insert or remove, is not merely measuring a particle. It is reaching backward through time and shaping what the particle was throughout its journey. The choice you make at the end is a constraint on the whole history. The particle never had a definite state in between, because the solution to the boundary value problem was not complete until both boundaries were specified. The particle existed in a kind of temporal limbo, open at both ends, until the final measurement closed the problem. This resolves one of the deepest puzzles in quantum mechanics, quantization. Why do quantum systems come in discrete energy levels rather than continuous ones? In the boundary value picture, quantization emerges naturally. Only certain solutions satisfy both boundary conditions simultaneously, just as a guitar string only vibrates at certain frequencies given its fixed endpoints. The future constrains which past states are even possible. The implications are difficult to absorb all at once. If Wharton is right, every quantum experiment ever performed is a collaboration between the experimenter's initial preparation and their final measurement choice. The particle does not travel a predetermined path from the first to the second. The entire trajectory, the whole history, is written by both boundaries together. And there is one more implication. If the future measurement genuinely constrains the past state, then quantum mechanics is hiding a massive secret about how the universe is connected across time. A secret that the famous Bell theorem was about to expose in the most dramatic possible way. In 1964, a physicist named John Bell sat down and proved something that most physicists would have considered impossible. He proved that the universe cannot be both local and realistic. Those two words carry enormous weight. Local means that objects are only directly influenced by things in their immediate vicinity, that no influence travels faster than light. Realistic means that particles have definite properties before anyone measures them, that the outcome of a measurement reveals a pre-existing fact rather than creating one. Both of these assumptions seem, obviously, trivially true. They are the bedrock of common sense. Bell proved that if quantum mechanics is correct, at least one of them must be false. The proof was mathematical. The experiments came later, and they were devastating. In the years that followed, physicists tested Bell's prediction using pairs of entangled particles fired in opposite directions toward detectors that were set to measure them in different ways. The results were unambiguous. The correlations between the two distant detectors violated Bell's inequalities by exactly as much as quantum mechanics predicted, and they did this even when the detectors were so far apart and the measurements so fast that no signal traveling at the speed of light could have coordinated the outcomes. The particles seemed to know what the other particle was being asked instantaneously across any distance. In 2015, 3 independent experimental groups in Delft, at the National Institute of Standards and Technology, and in Vienna, performed loophole-free tests. Every escape route was closed. The violation held. 3 of those experimenters, Alain Aspect, John Clauser, and Anton Zeilinger, were awarded the Nobel Prize in Physics in 2022. The universe is, beyond any reasonable scientific doubt, doing something that cannot be explained by local realism. This leaves physics with a crisis and a choice. Option 1. Abandon locality. Accept that the universe allows instantaneous influences across arbitrary distances. This is deeply uncomfortable because it conflicts with the spirit of relativity and offers no mechanism for how the influence propagates or why it cannot be used to send signals. Option 2. Abandon realism. Accept the Copenhagen interpretation's position that particles have no definite properties before measurement. This solves the mathematics, but leaves the underlying reality unexplained and, to many physicists, unexplainable by design. It substitutes silence for understanding. There is a third option. It is more radical than either of the others, and it has been gaining serious attention among physicists who refuse to give up on either locality or a real picture of the world. Retrocausality. If causal influences can travel backward in time as well as forward, then the apparent non-locality of quantum mechanics dissolves. The correlations between distant detectors do not require instantaneous action across space. Instead, the future measurement choices send influences backward in time to the moment when the particles were created, coordinating their properties right there, locally, at the source. No spooky action at a distance, just action at a distance in time. The locality crisis that Bell unveiled may be pointing us not toward a faster-than-light universe, but toward a universe where time itself is more permeable than anyone imagined. And the proof that retrocausality can dissolve Bell's paradox hinges entirely on one quiet assumption that Bell made, and that almost nobody noticed for decades. There is a hidden assumption in Bell's theorem, and almost nobody talked about it for decades. Bell's proof rests on several premises. The most famous are locality and realism, but there is a third assumption, quietly embedded in the mathematics, one that Bell himself acknowledged but did not emphasize. It is called measurement independence, and it states something that sounds obviously true: the properties of a particle, its hidden variables, are statistically independent of whatever measurement setting the experimenter will choose in the future. In plain language, the way a particle is set up in the past has nothing to do with how you decide to measure it later. The particle and the detector are strangers until the measurement happens. This seems so obvious, it barely deserves to be called an assumption. Of course, the particle in the past does not know what measurement you will make in the future. Information does not travel backward in time. So this premise was treated as unassailable, built into Bell's theorem like a foundation stone, and generations of physicists did not look at it twice. But if causal influences can run backward in time, the assumption collapses. Here is what that means concretely. Imagine you create two entangled particles at a source and send them flying toward detectors. The detectors are far apart. You choose the measurement settings, perhaps by flipping a coin, perhaps by consulting a random number generator after the particles are already in flight. In the standard picture, your future choice cannot possibly affect the particle's hidden properties, because the choice happens after the particles were prepared. In a retrocausal picture, your future choice sends an influence backward through time to the moment of preparation. The particle's hidden properties, whatever underlying variables determine their outcomes, are shaped by your future measurement decision. The two events, preparation and measurement, are not independent at all. They are connected through backward causation in a way that perfectly coordinates the outcomes without any need for faster-than-light signals. The correlations that violate Bell's inequalities are explained not by spooky action across space, but by causal influence across time. This is theoretically confirmed as a logically consistent option. It does not require abandoning locality. It does not require abandoning realism. It requires accepting only that the causal arrow of time is not as strictly one-directional as we assumed. Philosopher Huw Price and physicist Wharton formalized this in a 2021 paper, showing that the apparent non-locality of Bell experiments can be reframed as a collider bias, an artifact of ignoring the retrocausal influences that connect both measurement events to the shared past of the particles. The universe looks non-local from inside time. From outside time, from the block universe perspective, it is local throughout. There is something almost vertiginous about this. The most famous proof in the history of quantum foundations, the theorem that seemed to prove the universe was strange beyond rescue, may have been pointing at a different strangeness all along. Bell did not prove non-locality. He proved that one of three things must go: locality, realism, or the independence of the past from the future. Physicists have spent decades arguing about which of the first two to sacrifice. The retrocausal program quietly proposes the third, and then two researchers sat down in 2017 and proved something even more direct. They proved that the arrow of time itself, applied to quantum systems, leads straight to retrocausality. There was no longer any place to hide. Matthew Leifer and Matthew Pusey set out in 2017 to ask a question that nobody had quite asked before. Bell's theorem, as everyone knows it, concerns space. Two particles fly apart. Two detectors, separated in space, measure them. The correlations are too strong to be explained by any theory that respects locality and realism. The violation is spatial. The detectors are side by side in space, far apart, each doing its measurement at the same moment. But quantum mechanics also produces correlations across time. A single particle is measured twice, first at one moment and then at a later moment. The correlation between those two measurements, the way the first outcome relates to the second, also has a mathematical structure. Leifer and Pusey asked, can those temporal correlations be explained by a theory that is both time-symmetric and free of retrocausality? The question sounds abstract. The answer was not. The answer was no. They constructed a temporal analog of Bell's inequality, a mathematical bound that any time-symmetric theory without backward causation must obey. Then they showed that quantum mechanics violates that bound in exactly the same way that quantum mechanics violates the original spatial Bell inequalities. The violation is not a small discrepancy, not a statistical edge case. It is as clear and as large as the spatial Bell violations. The violation follows directly from the structure of the theory itself. This is a published result in the Proceedings of the Royal Society, peer-reviewed and unchallenged at the level of the mathematics. What it says is this: if you take quantum mechanics seriously, and if you take time symmetry seriously, then retrocausality is not one option among many, it is the only option. A time-symmetric quantum mechanics without backward causation contradicts the experimental predictions of the theory itself. Pause on that for a moment. The same experiments that prove the universe is non-local in space also prove, when read through a time-symmetric lens, that the universe is retrocausal in time. The Nobel Prize experiments, the loophole-free Bell tests, the results that shook physics in 2015, carry a second implication that most people have not yet registered. Leifer and Pusey were careful to note that their result does not prove retrocausality outright. It proves that if you want a time-symmetric interpretation of quantum mechanics, you must accept retrocausality. You can still escape by choosing an interpretation that is explicitly time-asymmetric, like the Copenhagen interpretation, which simply refuses to say anything about what happens between measurements. That silence is itself a philosophical position. The escape is available. It just costs you the ability to say anything about quantum reality at all. The mathematical picture is now complete in outline. Cramer showed that the formulas already contain backward-in-time waves. Price showed that time-symmetric laws demand retrocausal options. Wharton showed that quantum mechanics works as a two-boundary problem. Leifer and Pusey showed that temporal Bell inequalities are violated, sealing the logical case. What remains is the deepest question of all. Where does the future that reaches back actually come from? How can something that has not happened yet exert any influence on the present? The answer, built into Einstein's greatest achievement, may already be waiting, and it will change the way you think about every moment you have ever lived. Einstein gave us something more disturbing than gravity bending light. He gave us the end of now. In special relativity, two observers moving relative to each other do not agree on which events are simultaneous. For an observer at rest, two explosions might happen at exactly the same instant. For an observer streaking past at high speed, one explosion happened before the other. Both observers are correct within their own reference frames. There is no absolute truth about which event came first. Simultaneity is not a fact about the universe, it is a fact about the observer. This has a consequence that physicists absorbed quickly, and the rest of us have not fully absorbed yet. If there is no universal present, then there is no universal boundary between past and future. What is in your future is already in someone else's past, depending on how fast they are moving relative to you. The future, for some observer, somewhere in a valid reference frame, already exists. The future is already there. It is already part of the fabric of the universe. It is simply not yet visible from where you are standing. This leads to the block universe. The technical name is eternalism, or the B theory of time. The idea is that the universe is a four-dimensional object, extended in 3 dimensions of space and 1 dimension of time, and that all of it, every moment that ever was and ever will be, exists equally and simultaneously as part of that 4-dimensional structure. The past is real, the future is real. The present is simply the label we give to the cross-section of the block that we happen to occupy. Hermann Weyl, one of the great mathematicians of the 20th century, expressed it this way: the objective world simply is. It does not happen. Time is not a river flowing from past to future. It is a direction in a landscape, and all of the landscape exists at once. This is confirmed physics in the sense that special relativity is confirmed physics. The relativity of simultaneity is not controversial. Its philosophical implication, the block universe, follows from it as cleanly as a shadow follows a lamp. And here is why it matters for retrocausality. In a block universe, the future influencing the past is not strange at all. The future already exists. Both the earlier event and the later event are fixed, equally real, equally present in the 4-dimensional structure of spacetime. The question of which one caused the other is a question about the geometry of the block, about which constraints connect which events, not a question about something changing or reaching back through a flowing river of moments. Ken Wharton's all-at-once models fit perfectly here. The quantum event is a constraint satisfaction problem within the block, shaped simultaneously by the conditions at both temporal ends. The future measurement apparatus does not retroactively change the past. The past and the future are both parts of a single, self-consistent, four-dimensional object that simply is. The block universe does not merely allow retrocausality, it makes retrocausality geometrically natural, and one physicist, the greatest of the century, said something about time that was his honest, considered assessment of reality after decades of living inside these equations. It was physics, and nothing softer. On the 21st of March, 1955, Albert Einstein received word that his oldest friend had died. Michel Bessot and Einstein had known each other for more than 50 years. They met in Zurich in 1896, when both were students, and their friendship had outlasted every upheaval that the 20th century produced. It was Bessot who listened when Einstein was working through the ideas that would become special relativity. It was Bessot who walked home with Einstein one evening in 1905, talking through the problem of simultaneity, and to whom Einstein gave credit in the published paper for that conversation. Bessot died in Geneva at the age of 81. He died just 1 month before Einstein would die in Princeton. When Einstein wrote to the Bessot family to offer his condolences, he said something that has been quoted ever since, though usually without the full weight of what he meant. He wrote, "For us physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." People sometimes read this as a poetic consolation, a gentle way of suggesting that the dead are not truly gone, that Bessot in some sense still exists in the amber of the past. But Einstein was not writing poetry. He was writing as a physicist. The block universe is not a metaphor in his framework. It is the literal content of special relativity. Time does not flow. The universe does not unfold. It is a static, four-dimensional structure in which every moment exists on equal footing, and our experience of moving through time is a feature of consciousness navigating that structure, not a feature of the structure itself. The distinction between past, present, and future is an illusion because those categories are observer-dependent, not built into the fabric of reality. The future exists. It is as fixed as the past. We simply have not experienced it yet from our particular position in the block. Einstein spent the last years of his life deeply uncomfortable with quantum mechanics, famously arguing that God does not play dice, that the theory must be incomplete, that there must be hidden variables underneath the statistical predictions. He was wrong about the conclusion, as Bell's theorem and subsequent experiments confirmed. But the instinct that drove him, the belief that there must be a more complete description of reality lurking beneath quantum probabilities, was precisely the same instinct that drives the retrocausal program today. He was looking for the hidden structure. The retrocausal theorists are looking at the same wall from a different angle. Einstein never reconciled quantum mechanics with relativity to his satisfaction. He died without resolving the tension. The letter to the Bessot family points at what such a reconciliation might require, a framework in which the future exists as firmly as the past, in which particles thread their way through a four-dimensional structure constrained at both ends, their apparent randomness a shadow cast by the full geometry of spacetime. The block universe makes retrocausality geometrically natural, but it is not the only model of time that physicists and philosophers have proposed. There is a rival, one that wants to preserve something that Einstein sacrificed, the openness of the future. And the argument about which model is correct cuts to the deepest question in all of physics. Not everyone accepted Einstein's conclusion. The block universe, attractive as it is mathematically, carries a cost that some philosophers find too high. If the future already exists in the same sense that the past exists, then in what sense is anything genuinely open? In what sense do choices matter? In what sense does anything happen at all? rather than simply being the case, frozen into a four-dimensional solid that simply is. These are old philosophical questions, and the block universe answers them by dissolving them, which is not an answer everyone finds satisfying. There is an alternative, the growing block universe. In this model, the past and the present are equally real. They are fixed, laid down, permanent features of the temporal landscape. But the future does not yet exist. The future is genuinely open. As each moment becomes the present and then recedes into the past, the block grows. New slices of reality are added at the leading edge of time. The future is not a fixed destination. It is unwritten space waiting to receive the next moment of actuality. This picture preserves intuition. It allows us to say that the future is genuinely undetermined, that choices are real, that something is at stake in what happens next. It feels closer to lived experience than the frozen four-dimensional solid of full eternalism. But the growing block universe has a problem, and the problem comes from the same source as the block universe itself, special relativity. For the growing block to work, there must be a well-defined boundary between the fixed past and the unwritten future. There must be a universal now, a leading edge of the growing block that marks what has happened from what has not. But special relativity eliminates universal simultaneity. Different observers, moving at different velocities, disagree about which events are simultaneous. What is in the future for one observer is already in the past for another. If there is no universal now, there is no universal leading edge. The growing block requires exactly the thing that relativity forbids. This is a genuine problem, not a technicality. Philosophers have spent decades trying to formulate a growing block universe that is compatible with special relativity. The attempts are ingenious. None of them is fully satisfying. The most natural formulation always requires picking a preferred frame of reference, a privileged observer whose present defines the edge of the block, and relativity explicitly denies that any such observer is privileged. The growing block also makes retrocausality harder to accommodate. If the future does not yet exist, then in what sense can the future exert a causal influence on the present? A cause requires a real entity doing the causing. If the future measurement choice is genuinely unreal at the time of the past event, then the retrocausal picture loses its foundation. The block universe, whatever its philosophical costs, at least provides a coherent scaffold for the retrocausal framework. The future measurement exists in the block. The past event exists in the block. The constraint between them is a feature of the four-dimensional geometry. No reaching back is required, because nothing is traveling anywhere. Everything simply is. The debate between the block universe and the growing block is unresolved, but it is not purely philosophical. It connects directly to one of the deepest experimental puzzles in all of physics. A puzzle that sits at the boundary between cosmology and quantum mechanics, and that may be the most important clue retrocausality has yet offered about the structure of reality. There is something deeply strange about the way time works, and it has been hiding in plain sight for over a century. Every fundamental law of physics runs equally well in both temporal directions. Take any physical process, any collision, any interaction, any wave propagating through space, and reverse the direction of time in the equations. You get another valid physical process. Electrons repel each other identically whether time runs forward or backward. Gravity pulls the same way in either direction. Light bends around massive objects without caring which end of the timeline you start from. The laws themselves are time symmetric. This is established, confirmed, deeply verified physics. And yet, you have never watched a broken egg reassemble itself. You have never seen smoke flow back into a chimney. Time flows in one direction with an absoluteness that feels like a law of nature. The resolution to this contradiction is one of the great intellectual achievements of 19th century physics, thermodynamics. There are vastly more ways for a system to be disordered than ordered. An egg smashing on the floor produces millions of configurations of broken shell and scattered yolk. Reassembling those fragments would require finding the one configuration among millions that produces a whole structure, and time-symmetric laws have no tendency to find that particular arrangement over any other. Entropy, the measure of disorder, almost always increases. This is the arrow of time. Entropy increases, and that increase defines which direction is forward. But here is the question thermodynamics itself cannot answer. Why was the universe in such an extraordinarily ordered, low-entropy state at the beginning? The Big Bang produced a universe of almost perfect uniformity, almost the minimum possible entropy consistent with the energy available. From that improbably ordered starting point, following time-symmetric laws, entropy has been increasing ever since. The arrow of time is real. It is just not a fundamental law. It is a consequence of where things started. Everything we call the arrow of time, memory, causation, the entire sense that the past is fixed and the future is open, follows from that one initial condition. This matters enormously for retrocausality. If the arrow of time is thermodynamic and emergent rather than fundamental and built into the laws, then at the level of individual quantum events, there is no preferred direction. A single photon traveling between an emitter and a detector does not experience entropy. It does not generate heat. The thermodynamic arrow does not apply to it. At that scale, the time-symmetric laws are all there is. If the laws are symmetric and the arrow is merely statistical, then the question of whether a single quantum particle's past was shaped by its future measurement is not forbidden by any fundamental rule. It is forbidden only by the same statistical reasoning that forbids broken eggs from reassembling. And statistics, unlike laws, can be violated at the quantum level, where the numbers of particles involved are small enough for fluctuations to matter. The arrow of time is an emergent feature of large collections of particles. The microscopic world, where quantum mechanics lives, may have no preferred direction at all. And if the past and future are equally open to causal influence at the quantum level, then the retrocausal picture is not fighting against the laws of physics. It is simply taking those laws seriously in a domain where the emergent illusion of a one-way clock has no authority. The universe, at its deepest level, may be a place where before and after are not opposites. They are mirrors. Here is the question that makes physicists go quiet at dinner parties. If the future can influence the past, does a human being still have genuine choices? Think about what retrocausality actually claims. A physicist in a laboratory chooses how to measure a photon. That choice, made at a specific moment, reaches backward through time and shapes what the photon was doing before the measurement happened. The physicist's decision is the cause, the photon's past behavior is the effect, and the effect comes before the cause. So ask the obvious question: was the physicist really free to choose differently? Or was the choice itself somehow inevitable, locked in by the very backward influence it was supposed to produce? Philosopher Huw Price at Cambridge University has thought about this longer than almost anyone, and his answer is worth understanding carefully. Retrocausality, he argues, is actually the option that preserves free will rather than destroying it. That sounds strange until you see the comparison he is making. The real threat to free will is something called superdeterminism. In a superdeterminist universe, everything that has ever happened, including every thought you have ever had, every preference you have ever felt, and every experiment any physicist has ever designed, was fixed at the moment of the Big Bang. The measurement settings in a quantum experiment are correlated with the particle properties being measured through common prior causes. Both were predetermined by the same initial conditions billions of years ago. Superdeterminism explains the quantum correlations without retrocausality or action at a distance. It comes at a cost that most scientists find unbearable. If superdeterminism is true, science itself becomes impossible. An experimenter who cannot genuinely choose between two different setups cannot actually test anything. The experiment is theater, and the outcome was scripted before the universe had its first atom. Retrocausality takes a different path. The experimenter's choice is real, the freedom is genuine. The physicist picks a measurement setting, and that choice exerts causal influence in both directions through time. Forward into the detector, backward to the particle's earlier state. The choice is free, and it matters in ways that extend beyond what classical physics imagined. But what does this mean inside the block universe? Recall that in the four-dimensional block universe, all events already exist as fixed points in spacetime. The physicist's choice is already there, laid out in the fabric of the universe alongside every other event. Does a fixed future choice count as free? Price says yes, and the reasoning is subtle. Freedom does not require that your choice be undetermined by the laws of physics. It requires that your choice is genuinely yours, that it reflects your deliberation and will, and that it actually causes what comes next and what came before. In the block universe, the physicist's choice does all of those things. It is fixed as a fact, but it is also genuinely causal. The fixedness is not imprisonment. It is simply what it looks like from the outside of time. This is confirmed as a philosophical position, though whether it resolves every intuition about freedom remains genuinely open and contested. What is not contested is the experimental fact underneath it all. Something connects a future choice to a past event. Whatever we call that connection, it is real. And whatever it means for free will, the implications grow stranger still, because quantum mechanics has a remarkable built-in safeguard, and discovering what it protects against opens an entirely new layer of this story. Suppose you have just learned that future measurements influence past particle states. The first thing most people wonder is whether you could use this to send a message backward through time. Warn yourself about a mistake. Communicate the outcome of tomorrow's event to someone standing in today. Quantum mechanics does not allow it. The prohibition is not accidental. It is written into the mathematical structure of the theory at a level so deep that every interpretation of quantum mechanics, no matter how radical, must respect it. This is confirmed, tested, and has held without exception across every experiment ever performed. Here is how the protection works. In the delayed choice quantum eraser, the interference pattern that reveals wave behavior is not sitting in the raw signal photon data, it is hidden. When you look at the complete record of where signal photons landed, you see only a blur, no pattern, no interference fringes, nothing that would tell you anything about whether the idler photons' which path information was later preserved or erased. The pattern only emerges when you compare the signal data with the idler detector results. You must take both records, match them moment by moment, and sort the signal detections into groups based on which idler detector fired. Then the interference pattern appears in the subset corresponding to erased idler detections. It was there all along, but invisible without the future information. An observer living in the past, watching only the signal photons land on the screen, has no way to see anything unusual. The screen looks exactly as ordinary physics would predict. There is nothing to read. No signal arrives. The backward influence is real, but it arrives in a form that no one in the past can decode without data that has not yet been collected. Physicists call this the no retrosignaling principle. Some also call it the no signaling theorem. It is mathematically equivalent to the requirement that quantum mechanics cannot be used to send information faster than light. Both prohibitions come from the same place in the equations, and both have been confirmed without exception. This connects to an idea from a completely different corner of physics, the Novikov self-consistency principle, which emerged from theoretical work on time travel in general relativity. Physicist Igor Novikov proposed that any event that travels backward in time must be consistent with the history it enters. You cannot go back and kill your grandfather, because if you had killed him, you would not exist to go back. Only self-consistent loops are permitted. Quantum retrocausality obeys the same discipline. The backward influence is real, but it never creates a paradox. The information that flows back through time is always encoded in a form that cannot be exploited by anyone in the past. The universe permits the influence and prohibits the abuse simultaneously. This is elegantly self-protecting. And for most physicists who accept retrocausality as physically meaningful, this protection is exactly what makes it plausible. A retrocausal universe is not a universe of paradoxes. It is a universe of constraints, globally consistent, where every event is compatible with every other event across all of time. But not everyone finds this satisfying. There are serious physicists who argue that the whole framing is a mistake, that retrocausality is a ghost conjured by sloppy interpretation, and their critique is surprisingly hard to dismiss. The first skeptical objection to retrocausality was philosophical. The Copenhagen interpretation said that asking what a particle was doing before measurement is simply a category error. There is no answer to give because there is no fact to describe. The second objection is sharper. It is mathematical. In 2024, physicists Maarten Voyager and Jan van Nieuwen published a careful analysis of delayed choice experiments in a peer-reviewed journal. Their finding was striking. They showed that if you take the standard delayed choice quantum eraser and rearrange the order of its steps, changing which event happens first and which happens second, the final quantum state you end up with is identical. The mathematical outcome does not depend on the time ordering at all. This is a genuinely serious challenge. If the order of events does not change the final state, then in what sense is one event causing another, forward or backward? The apparent retrocausality may be an artifact of how we narrate the experiment in time, rather than a real feature of the underlying physics. Think of it this way. When you watch a film in a cinema, the story appears to unfold from beginning to end. Events seem to cause other events, but the entire film exists on the reel before you enter the theater. The causal story you experience is projected onto something that was already complete. Voyager and van Nieuwen are suggesting that delayed choice experiments may be similar. The time-ordered narration is real for us, but the underlying physics is entirely indifferent to it. This is still a minority view, and the debate is genuinely unsettled, but the argument is compelling enough that leading physicists take it seriously. The challenge does not stop there. Physicist Sabine Hossenfelder, whose critiques of fashionable physics ideas have earned her a wide following, has argued forcefully that popular accounts of the quantum eraser have fundamentally misrepresented what the experiment shows. The erasure, she argues, does not remove which path information from the past. It demonstrates the structure of quantum correlations, which are strange and non-local, but do not require backward causation to explain. Ordinary textbook quantum mechanics, she and others argue, predicts every result of every delayed choice experiment ever performed. There is no residue left over that demands something extra. The strangeness is real. The retrocausality is an optional interpretation layered on top of mathematics that already works perfectly without it. The honest answer, the one that experimentalists and theorists alike must give when pressed, is that this objection has not been fully answered. The experiments are real. The correlations are undeniable. What remains genuinely ambiguous is their deeper meaning. Two physicists can examine the same data from the same laboratory and arrive at entirely different conclusions about whether the future has influenced the past. This is the sign that something genuinely deep and unresolved sits at the foundation of the theory. Physics has not failed here. It has simply found a question that its current tools cannot yet resolve. And while retrocausality is fighting for its life against these critiques, another interpretation of quantum mechanics has been quietly building a case that needs no backward causation at all, and whose implications are, in some ways, even more unsettling. In 1957, a graduate student at Princeton University named Huw Everett III submitted a doctoral thesis that his advisor, John Wheeler, described as both brilliant and profoundly uncomfortable. Everett proposed that the wave function never collapses, ever. In standard quantum mechanics, when you measure a particle, its superposition of possibilities collapses into a single outcome. One thing happens, the rest vanishes. Everett said this was wrong. What actually happens, he argued, is that every possible outcome occurs simultaneously. The universe splits. In one branch, the particle goes left. In another branch, the particle goes right. Both branches are equally real. The version of you who sees the particle go left is unaware of the version of you who sees it go right, because the two versions no longer interact with each other in any detectable way. This is the many worlds interpretation of quantum mechanics, also called the Everett interpretation. It remains one of the most debated ideas in all of physics, precisely because it is impossible to refute by experiment and deeply strange to contemplate. Here is what it means for the delayed choice experiments. In the many worlds framework, there is no collapse, no single outcome, and no special role for future measurements. When a photon passes through a double slit and then its entangled partner reaches a detector, every possible outcome of that detector measurement occurs in some branch of the wave function. The correlations between the signal photon and the idler photon are correlations between branches, not the result of any backward influence reaching from future to past. The interference pattern that appears in post-selected subsets of the data is, in this view, a reflection of entanglement structure between branches. There is no moment where a future choice determines a past behavior. There is only the global wave function, unfolding deterministically forward through time, splitting at every quantum event into all possible outcomes simultaneously. This is mathematically rigorous. It requires no retrocausality. It requires no backward-flowing influences. It requires no hidden variables or time-symmetric wave functions. What it requires instead is an almost incomprehensible proliferation of parallel realities. Every quantum event that has ever occurred in the history of the universe has branched the wave function into multiple versions. The number of parallel universes implied by this picture is so large it defeats any attempt to imagine it. A single photon passing through a double slit creates two branches. Every interaction inside a detector creates more. In the time it takes to run a single quantum experiment, the number of branches grows to a figure with more digits than atoms in the observable universe. Whether this counts as a simpler explanation than retrocausality is itself a matter of genuine disagreement. Many physicists find the branching extravagance philosophically more costly than allowing causal influences to run backward in time. Others find retrocausality more troubling than a vast landscape of parallel realities they can never access. Neither camp can point to an experiment that would settle the argument. This is the uncomfortable truth about quantum foundations. Multiple completely different pictures of reality make identical experimental predictions. The universe, at its deepest level, appears to permit multiple logically consistent stories about what is actually happening. But saying all stories are equally credible is also too easy. Some of those stories are currently under severe strain, and the most detailed recent assault on retrocausality came from a group of researchers who tested the idea by trying to build it in precise mathematical detail and ran into something they did not expect. Sometimes the most damaging attack on an idea comes from people who were originally trying to make it work. Researchers associated with the University of Bristol, including physicists with serious credentials in quantum foundations, set out to construct an explicit model of retrocausal quantum mechanics. They wanted to build a concrete mathematical framework, a local realist theory in which future measurement settings send influences backward through time to coordinate the particle outcomes. If retrocausality is a genuine feature of reality, such a model should exist and should reproduce the full set of quantum predictions. They found something troubling. When they attempted to enforce full consistency across all the correlations the model needed to reproduce, the models began to contradict themselves. The backward-flowing influences that resolved one set of quantum correlations created inconsistencies in another set. When they tightened the mathematical constraints to eliminate those inconsistencies, the models began producing predictions that conflicted with what experiments actually show. This is a serious result, and the retrocausality community has not fully answered it. The critique, available in preprints and journal papers circulating between 2022 and 2025, suggests that local realist retrocausal models face a structural problem. The freedom they gain by allowing backward causation is not quite enough freedom to accommodate everything quantum mechanics actually predicts. Defenders of retrocausality have pushed back, arguing that the Bristol constraints are too strong, that the models being tested are merely one variety of retrocausal model, and that more general frameworks may escape the contradiction. Ken Wharton, whose all-at-once Lagrangian approach treats the quantum system as a boundary value problem solved across all of time simultaneously, argues that the Bristol critique targets a specific class of models and does not apply to his formulation. Matthew Leifer and Matthew Pusey, whose time-like Bell inequality established retrocausality's mathematical necessity under time symmetry assumptions, have likewise argued that the Bristol analysis begins from premises narrow enough to exclude the most promising retrocausal approaches before the argument even begins. The debate is unresolved. Both sides continue publishing. Both sides claim the evidence favors their reading. What this reveals about science is worth pausing on. The popular picture of science as a clean march from ignorance to knowledge is a serious simplification. At the frontier, the picture looks more like this: a genuine experimental anomaly, multiple theoretical frameworks, each capturing something real, each facing difficulties the others do not, and a community of talented researchers who cannot yet agree on what the data actually means. That is physics working correctly. The discomfort is not a sign of failure, it is the sign that the question is real. Retrocausality is alive. It is under serious fire. It is generating predictions that can, in principle, be tested, and researchers on both sides are building toward experiments that may eventually force a resolution. The testing is entering a new phase because the past 2 years have brought a wave of results and proposals that are pushing the question toward ground it has never before reached. Something stranger and more hopeful is coming. The machinery of modern quantum physics is being aimed directly at the problem of time itself, and the experiments it is producing are unlike anything this debate has seen before. Physics moves fast when it finds a sore spot, and the question of whether time is truly one-directional has become one of the most productive sore spots in the field. In 2025, researchers at the Austrian Academy of Sciences and the University of Vienna announced a result that sent ripples through the quantum foundations community. They demonstrated what they called a quantum rewind protocol. Using carefully engineered sequences of quantum operations, they were able to return photons to their earlier quantum states the researchers themselves had no advanced knowledge of. With an accuracy exceeding 95%, the team's lead researcher described it simply. "The protocol is like rewinding a film," he said, but without ever having seen the frames. The photon returns to where it was without any classical record of where that was. This is experimentally confirmed. The protocol works. What it means for retrocausality is more nuanced. It demonstrates that quantum evolution can be reversed with extraordinary precision, which is consistent with the time-symmetric picture of quantum mechanics, but does not by itself prove that causal influences flow backward. What it does prove is that the direction of time at the quantum scale is far less rigid than classical intuition assumes. And if time is negotiable at the small scale, the larger question of retrocausality begins to look less impossible. In the same period, a paper published in a major entropy journal at the opening of 2026 explored the logical structure of Bell tests through the lens of what physicists call predictive incompleteness. The idea is that the quantum state alone is not sufficient to specify a probability distribution for measurement outcomes unless you also specify the future measurement context. The future context is load-bearing, mathematically necessary to make the predictions work. This framing aligns naturally with retrocausal models, where future choices impose boundary conditions on past states. Separately, researchers at the University of Surrey published evidence in early 2025 that even open quantum systems interacting with their environment, can display equations that remain time-symmetric. The memory structure of these systems, a mathematical object called the memory kernel, was found to be symmetric in time. This suggests that at the microscopic level, even messy quantum systems may carry no intrinsic preference for one time direction over another. What each of these results shares is a direction. The field is moving away from pure philosophy and toward falsifiable predictions. Proposals now circulate for extended quantum eraser experiments that would, if strong retrocausality holds, show the interference pattern appearing in raw, unconditioned data rather than only in post-selected subsets. If that ever happened, it would be unambiguous. The future would be demonstrably shaping the present in real time, with no interpretation needed. It has not happened yet. That null result matters too, because it continues to constrain how powerful any backward influence can be. But the fact that such experiments are being seriously designed and proposed marks a genuine shift. The question of time is becoming empirical in ways it never was before, and the grandest version of this question was posed decades ago by the man who started the whole inquiry, looking past any laboratory bench all the way to the edge of the visible universe. John Wheeler was not a timid thinker. He coined the phrase black hole before anyone else thought to use it, supervised Richard Feynman's doctoral work, and spent decades asking questions that made other physicists uncomfortable. But even by his own standards, the cosmic version of his delayed choice experiment was something else entirely. Here is the setup, and every word of it is confirmed observational fact. When light from a quasar, located billions of light years away, travels toward Earth, it sometimes passes close to an intervening galaxy. The gravity of that galaxy bends the light, splitting it into two separate paths that curve around opposite sides of the galaxy and then converge toward Earth. The result is a gravitational lens, and we observe them routinely. The two paths of light arrive at Earth from slightly different directions. This is, Wheeler pointed out, a cosmic double slit. The quasar is the light source. The galaxy is the barrier. Earth is the screen. The light has been traveling for perhaps 8 billion years. It left its source before our planet existed, before any organism capable of asking a question had ever drawn breath anywhere. Now an astronomer on Earth makes a choice. If the astronomer uses a telescope pointed at one of the two lensed images, they detect photons arriving from one path or the other. Particle behavior, which path information is available. If instead the astronomer uses an interferometer that combines the two paths before detection, they see interference fringes, wave behavior. The two paths cancel and reinforce each other in a pattern that stretches across the sky. Quantum mechanics predicts that the photon's past behavior, whether it traveled as a wave taking both paths simultaneously or as a particle committing to only one, is correlated with the measurement the astronomer chooses to make today. The astronomer's choice is made 8 billion years after the photon committed to whatever it did back then. And quantum mechanics says that commitment was not made until the measurement happened. This is not a thought experiment anymore. We observe gravitationally lensed quasars every time large telescopes examine the deep sky. The physics that governs this situation is the same physics that governed every laboratory delayed choice experiment ever performed. The experiment has not been executed in the full interferometric sense, because combining two paths separated by the angular scale of gravitational lensing requires an instrument that does not yet exist, but the equations are the same. The prediction is unambiguous. Wheeler drew the most radical conclusion he could from this. The astronomer's choice today participates in determining what that photon was doing billions of years ago. The present reaches back across time deeper than human civilization, deeper than the formation of the Earth, to shape an event at the far edge of the observable universe. The measurement is made inside a building, on a campus, by a person who ate breakfast this morning, and it is reaching back to before the dinosaurs, before the first fish, before the planet itself solidified out of its disk of dust. That is what the physics says. He called this the participatory universe. The implications of taking it seriously extend far beyond any single photon or any single astronomer's choice. They reach into the nature of reality itself, and into what it means to be a conscious being inside a cosmos that may require your participation to become fully real. John Wheeler spent the last decades of his life circling a single question. He phrased it many different ways, but its core never changed. He wanted to know why there is something rather than nothing, and he thought the answer might involve observers in a way that physics had never taken seriously before. His idea was this: the universe, at the quantum level, does not have definite properties until something interacts with it and forces a definite outcome. The interference patterns of delayed choice experiments, the weak values of Aharonov's two-state vector formalism, the backward-flowing confirmation waves of Cramer's transactional interpretation, all of these suggest that reality is not simply out there, pre-assembled, waiting to be discovered. It is brought into sharpness through interaction. Wheeler called this the participatory universe. Observers are not passive witnesses. They are participants in the creation of the physical facts they observe. This is confirmed in a limited but precise sense. At the quantum level, measurement does not merely reveal pre-existing properties. This is experimentally established beyond any serious dispute. The polarization of a photon, the spin of an electron, the path a particle takes through an interferometer, these properties are genuinely indeterminate before measurement. The act of measurement brings them into definite existence for the first time. What Wheeler proposed was that this participatory principle is not merely a feature of small laboratories. He believed it extends all the way back to the origin of the universe itself. Here is the argument, and it is one that serious physicists continue to engage with. The cosmic background radiation, the faint afterglow of the early universe, has been measured with extraordinary precision. Those measurements, made by instruments on Earth and in orbit, have established precise facts about the early universe. In Wheeler's framework, those measurements participate in determining what the early universe was. The present reaches back through billions of years of cosmic history and helps bring the past into definite existence. This is a genuinely contested philosophical position, and most working physicists do not follow Wheeler all the way to this conclusion. But the experimental facts that motivate it are real. The laboratory demonstrations of delayed choice are real. The correlations between present measurement choices and past particle behaviors are real, published, and confirmed. If you accept the logic at any scale, Wheeler argues, you must accept it at all scales. The universe is not a machine that ran and produced us incidentally. We are woven into its structure as the means by which it becomes real in any definite sense. Ruth Kastner, at the University of Maryland, working within the possibilist transactional interpretation, has developed a related picture. In her framework, the offer waves and confirmation waves that complete a quantum transaction are not yet real events in physical spacetime. They exist in a realm of quantum possibility, a pre-spacetime level of reality where outcomes are undecided. Measurement completes a transaction and lifts a possibility into actuality. The past becomes definitively real only when the future has participated in making it so. This picture of reality is radically different from anything classical physics ever imagined, and its consequences for how we understand ourselves as human beings embedded in a universe like this are just beginning to come into focus. Physics has a habit of arriving at conclusions that feel personal, even when they are entirely impersonal. The Earth is not the center of the universe. Time does not flow at the same rate for everyone. Matter is mostly empty space. Each discovery has been absorbed slowly, over generations, until it stopped feeling like an insult and started feeling like a wonder. The retrocausal picture of quantum mechanics is the next candidate for that kind of absorption. If the future can influence the past, even in the constrained, paradox-free way that quantum mechanics allows, then the universe is a fundamentally different kind of place than the one classical physics described. Classical physics imagined a cosmos like a long falling of dominoes. The first domino fell at the beginning of time. Each subsequent event was pushed forward by the last. The universe was a chain, and you were a link in it, shaped by everything that came before and shaping only what came after. In a retrocausal universe, the structure is different. The universe is more like a four-dimensional object whose pieces are mutually consistent with each other across all of time. The past influences the future, and the future influences the past. Every event is constrained by what came before it and by what comes after it. The system is solved globally, not step by step. Your choices exist inside that structure. This is confirmed to the extent that free will exists at all in any theory of physics. Retrocausal models preserve it as well as any other. What changes is the direction in which those choices might ripple. Think about what you do on any given day. You make a measurement of sorts every moment. You look at something and bring it into focus. You attend to one thing and ignore another. You ask a question, and by asking it, you frame what kind of answer is possible. If Wheeler is right, that measurement participates in creating physical reality, then these acts of attention are not merely passive reception, they are participation. Most of that participation operates at scales far above anything quantum. Your daily choices are not steering photons through interferometers. But the principle that the present moment is not merely receiving the past and transmitting to the future, but is embedded in a larger structure of mutual constraint across time, has a different quality to it than the domino model did. The domino model made you a product. Everything that shaped you was already decided. Everything you do will be decided by what was already done to you. There is a comfort in that. There is also a closure. The retrocausal block universe keeps you embedded in history while making the embedding more complex. The future is already there. Your choices are already part of the four-dimensional structure. And that structure, if Aharonov and Wheeler and Price are even partially right, is something in which all times participate in making each other real. The boundary between cause and effect, between before and after, may be far more permeable than it has ever appeared. And the question that follows from that is the deepest one this story has to offer. Here is what we know for certain. Physicists in Paris built an apparatus in 2007 that produced results exactly matching what John Wheeler predicted in 1978. Researchers in Italy sent photons to a satellite 1,500 kilometers above the planet and confirmed the same predictions hold across distances that should have made any light-speed signal impossible. A laboratory in Maryland in 1999 detected that a signal photon's past behavior is correlated with a measurement that had not yet been made when that behavior occurred. These experiments have been repeated, extended, checked for loopholes, and confirmed. The results are not in dispute. Here is what we do not know, what those results mean. Every serious interpretation of quantum mechanics makes identical predictions for every experiment ever performed. The Copenhagen interpretation says the particle had no definite properties before measurement, and the question of what it was doing earlier is meaningless. The many worlds interpretation says all outcomes occurred, and the correlations reflect entanglement between branches of a universal wave function. The transactional interpretation says a confirmation wave traveled backward through time from absorber to emitter, and the transaction completed in a single four-dimensional handshake. The two-state vector formalism says the particle was simultaneously shaped by a wave function from its past and a wave function from its future. Retrocausal models say the measurement setting in the future influenced the hidden variables of the particle in the past. Every one of those descriptions produces the same numbers. Every interference pattern, every Bell inequality violation, every weak value anomaly, predicted identically. The universe, at its most fundamental level, refuses to tell us which story is true. This has been called the measurement problem, the interpretation problem, the foundational crisis of quantum mechanics. It has been unresolved since the 1920s. The greatest minds of the 20th century looked directly at it and could not settle it, and every experiment since has deepened the experimental certainty while leaving the interpretive question exactly as open. Scientists proved something real. They proved the correlations exist. They proved that a future measurement choice is statistically connected to a past particle behavior in ways no classical theory can explain. They proved that any complete mathematical description of that connection requires either giving up locality, giving up realism, or allowing the future to influence the past. They did not prove which of those options is correct. That is the frontier. Science advances by making the question precise enough to become answerable. A century ago, no one could even formulate this question clearly enough to run an experiment. Now the experiments exist, the data is exquisitely precise, and the remaining question is about what the data means at the level of reality itself. Some physicists believe a new experiment will finally distinguish between interpretations that currently agree on everything. Others believe a conceptual revolution in how we think about time and causation is the only path forward. Others believe the question is malformed and will dissolve when we find better language. What is certain is that the picture of time as a simple river flowing from past to future cannot survive contact with these experiments. The universe, at its smallest scale, does not honor that picture. The future is present in the past in a way that classical physics never imagined. Wheeler said the past has no existence except as it is recorded in the present. He meant it as physics. We are still inside the question, and the question, it turns out, is the most beautiful place physics has ever found.